Hello and welcome. My name is Jean-Christophe Carrette. I am the head of technology of IMI Hydronic Engineering. Today, I will be presenting you the new revolutionary valve from IMI TA Smart. Hydronically, TA Smart is a control valve. What makes it completely different from standard control valves is the way it is controlled. Beyond traditional position control, it can operate in flow control mode or in power control mode. For enabling this, TA Smart is built from 6 essential parts. A valve body integrating an ultrasonic spool chamber, a C part, a smart box, an actuator, and 2 temperature sensors. In addition to the flow and power control modes that bring the balancing and control functions, TA Smart has outstanding measuring capabilities. It is able to continuously measure the flow, the supply and return temperatures, as well as the power with high accuracy. And it locks all this data in its embedded memory, as well as into the cloud through digital communication. A big part of TA Smart is its fundamental ability to continuously measure the flow rate passing through itself. And it does not do that just continuously, but also accurately, with high measuring accuracy all the way down to very small flows. This is particularly important because we know that heating and cooling systems operate under 20% of their flow for 70 to 80% of the respective operation time. TA Smart provides high accuracy of flow measurements according to this curve. It is very close to 3% of accuracy on the majority of the flow range and up to 5% down to 2% of the nominal flow. Some devices on the market, providing also flow measurement, indicate the delivered accuracy only above 20 to 25% of the nominal flow. That is a bit odd, considering that systems work under these conditions only a small fraction of their operation time. For temperature measurement, TA Smart uses 2 PT1000 temperature sensors, which are pair-calibrated to provide improved accuracy even at low delta T. Building on great measuring flow and temperature capabilities, TA Smart provides accurate power measurement in both heating and cooling applications with accuracy levels between 4 and 7% depending on the delta T. What is really unique and makes the design particularly exceptional is the fact that it is all incorporated in a very compact body, with a control valve just behind the ultrasonic spool chamber, while providing world-class accuracy. Speaking about compactness, TA Smart is incredibly compact. TA Smart DN32 is as much as 80% smaller than combined products on the market, and it has only 2 bodies to be fitted with no space requirement upstream. TA Smart DN65 and 80 have actually an F1 face-to-face length according to EN 558, with DN65 being up to 35% smaller versus competition. This significantly improves installation, especially in renovation projects, where you would be able to remove an old product and seamlessly fit TA Smart in the left space, without complicated additional fittings and pipe adjustments. TA Smart can control the flow down to an amazingly low 0.5% of the nominal flow, and this against a differential pressure as high as 400 kPa. It is flexible in terms of control modes, with 3 modes available: flow control, power control, or position control. And these control modes can be chosen via the iTunes smartphone app, using the local area network, or on the cloud if TSmart is connected to it. One of the great things is that all TSmart configuration and hydronic information are accessible directly via your smartphone, even without any bus communication or cloud connection. And it does not require you to bring any special equipment, cable or adapter. You only need your smartphone or a tablet. I'm going to show you briefly now how the TSmart operates and how it can be configured. Let me show you first the hydronic demo unit that we are going to use for this demonstration. We first have a TSmart on the pipe there that is followed by a microbubble separator and then a variable speed pump. The variable speed pump is going to be used to vary the differential pressure applied in the circuit. We have then a manual balancing valve which is there to simulate the presence of a terminal unit. And we get back to the TSmart. Obviously, we have got two temperature sensors with TSmart. One that is integrated in the body of the valve, and in this demo unit, it is measuring the temperature of the water running through this unit. This temperature of the water is relatively high as the pump is transferring heat to the water. The remote temperature sensor is actually not connected. We simply take the temperature of the room to create a virtual delta T between the water in the rig and the room. If I had to get the two temperature sensors in this demo unit, I would have needed to connect a boiler and a terminal unit for generating and absorbing heat, and that would have been quite more bulky than what I can show you now. Let's now try with the app. I'm now going to show you how to connect yourself to TSmart to read the main parameters and configure it. I'm starting the iTunes app, and I'm first having a welcome screen where I can start scanning for devices on the Bluetooth range. You can see that it immediately detects the TSmart 32 of the demo unit I have shown you. The flow can already be read, 1750 liters per hour, and I can connect myself to this valve. Once connected, I can read the live parameters of the valve, 1750 liters per hour, and a delta T of 12 degrees. Well, it's coming from the fact that there is one temperature probe in the valve, and it's measuring the temperature of the water. The water is heated up by the pump at 37 degrees. And then we get the remote temperature sensor outside. In this room right now, it is 25 degrees. So we are getting a delta T of 12 degrees. The fluid is set as being the water, and consequently from the flow and the delta T, we are getting a power of 25 kilowatts, a virtual power. Input signal to the valves is 10.3 milliamperes, and the current opening is 39%. The gauge that you can see there is a gauge that gives you the relative value of the flow compared to its target. The target maximum value is 3,500 liters per hour, as you can see. So we get about 50% of this value. I'm now going to change the signal to the valve with the small control box that I have here, and I'm going to reduce it to a value of about 4 milliamperes. You can see that the valve reacts to this and gives you the flow that is required. At 4 milliamperes out of 20, I should be around 20% of the set target, and you can see two graduation on the gauge, which give us what we need. One thing that we can also see very much in the behavior of such a valve is that it compensates for differential pressure variation that will happen in the hydronic network. And to simulate such variations, what I'm going to do now, I'm going to change the differential pressure generated by the pump. I'm going simply to jump in terms of speed of the pump from a relatively moderate to medium speed to a lower speed. I'm doing this, and as I receive a smaller differential pressure from the pump, instantaneously we get less flow available in the circuit, but the valve comes back and compensates for this variation of differential pressure. In the opposite of that, I can increase my differential pressure to the maximum speed of the pump, and you can see that instantaneously again, the flow increases, while the valve is going to compensate and bring me back to the original value, which is my target value. We are now going to look at the configuration. I will simply touch the configuration frame and look at the different options that are available to me. There are some parameters of configuration that allows me to indicate whether the valve is installed on supply or on return. I leave it where it was. And I can define, of course, the type of fluid that is being used as being one of the two glycols, monoethylene glycol or monopropylene glycol, but obviously right now I'm working with water. I come back there and I will enter now some control parameterization with control settings. In the control setting, I can see that the valve has been set for flow control with a control characteristic that is equal percentage. And this control characteristic is between the signal received by the valve and the flow that we'll try to achieve. This can be changed in this screen. There is then a control source. It can be analog or bus or direct remote configuration by the cloud. And then I could change also the analog signal. Here I can choose different type of signal. If the signal that I want to use is not of the type I wanted to use, I can change it there and receive instructions on what has to be done inside the smart box to switch from milliamperes to voltage. I can revert the signal, obviously, and also change the signal so that we are going to get 2 to 10 volts as an input. This is it. It's a brief demonstration of the different parameters that can be configured and read with the TS-Smart, with a very good view on what you are currently getting from the valve at the instant you read it. TS-Smart can be used anywhere you would use a two-way control valve, and you would benefit from detailed and accurate information about flow and energy usages. It is particularly adequate for applications like air handling units, crack units, heat exchangers, and injection control loops. And it is certainly key for equipping buildings where energy certifications are requested, energy cost is monitored, or reliability is critical. That is it for this presentation. Thank you for your attention.